So now we're going to go more deeply into tangent planes and normal lines, and we're going to see what can we use these tangent planes for. So we're going to refresh just way back in Calc 1. So if you remember back there, in Calc 1 we learned we could approximate a function. Say y equals f of x near a point x naught by using its tangent line. Okay. So if we have a visual, here is our xy plane. Here is our function. I don't know, maybe it does something like this. And if I want to approximate this particular function value, which has some x value associated to it, the y value would be plugging it into the function. What I can do is I can use the tangent line at that point. Just gonna move this a little bit so it's a little bit nicer. There we go. So we could use the tangent line because nearby the gap in between the function and the tangent line wasn't that big. And so if you wanted the equation of this tangent line, we can find that pretty quickly. The tangent line passes through the point x naught, and then the y coordinate would be the function evaluated at that point. And remember, the slope is just the derivative. So it has slope, which is the derivative evaluated at that x value. Okay. So the equation of the tangent line is the following. You take y and subtract the y coordinate of the point. It equals the slope times x minus the x coordinate of the point. And then we like our line just to be y equals all this stuff. So you just add this over, and this gives us our y is equal to the y value of the point plus the derivative evaluated at the point times x minus x naught. So this is the equation of our tangent line. So what I could say, because a line is much easier to evaluate than potentially exponential or trig functions, we could say these two were about equal to each other nearby this particular point. So ultimately, for values of x, near x naught, we can say that the function is about equal to this tangent line. Because all of these are constants. So if I want to find cosine of 5, all that would require me to do is plug in 5 for x in that tangent line. Okay. So this was called that linear approximation. So all that ends up happening when we're in 3 dimensions is we don't have a tangent line, we have a tangent plane. And we know that tangent plane to level surfaces dealt with the gradient vector or those partial derivatives. Realistically, this ends up being exactly the same. So it has a pretty analogous formula in two dimensions. If you also remember in Calc 2, you learned these are just the first two terms of the Taylor series at that particular value. Well, there's Taylor series for multivariable functions too. And so this just ends up being the first couple terms of the multivariable Taylor series. So we're going to go ahead and we're going to build this just so you can see again how this all ties in together. But I want to come up with the tangent plane. So likewise, we can use tangent planes to approximate a function of two variables. For these points x, y, near the point of tangency. Okay, so let's draw a nice picture. And I'll try to draw a different surface this time than my normal one. Maybe we've got kind of a circular looking thing going on here. Here is our function z, which is a function of x and y. And I'm going to find the tangent plane at this particular point. So this would lie on the surface like this. Okay. And this particular point, again, to just not muddle everything in there, this will be the point x naught, y naught, and then the z coordinate, which would be plug it into the function. So its projection in the xy plane is just x naught, y naught. What I need is the normal vector for this plane, n. And this has components a, b, and c. So I want to figure out what do these things have to be. And again, it really just ends up being that gradient vector because we know that's going to be orthogonal to our tangent plane. Okay? But I will show you how that comes about utilizing just this particular example. So what I can do is I can instead specifically look at certain directions. So if I look at the line here, that's going to run parallel to the x-axis, we'll call this line 1. And then if I look at this line here, parallel to the y-axis, this is line 2. We know, based on our partial derivatives, that line 1 has slope, which is the partial with respect to x at that particular point. And line 2 has slope, which is the partial with respect to y at that particular point. Okay? And we know these lines are going to be tangent to the surface, so these lines are going to lie in the tangent plane. So we're going to utilize that to our advantage. Now, realistically, we can do what we've already done, where we can use that gradient vector, but I'll show you just by creating the equation of our tangent plane and showing that the components in front of the x and y have to be these partial derivatives. Because realistically, I don't want to take a partial with respect to z because I have a function of x and y. So that partial gets kind of not as clear cut in this format. So ultimately, we need to find an equation for the tangent plane. we know a point it passes through, and we're trying to figure out what is this normal vector. So a plane that contains the point x naught, y naught, and then the z coordinate is just the function evaluated at these points, has the equation where we have a times x minus x naught, b times y minus y naught, and then c times z minus the z coordinate, which is the function evaluated at those points. Okay. Specifically, where n is this normal vector with components a, b, and c. What I want to do is just rewrite this so it's a little bit nicer, okay? So I can go ahead and I can move this to the other side, or I can move both of these over, doesn't matter. So this can ultimately be rewritten as the following. I'll go ahead and let the C component be on its own because that's the messiest looking one. And we'll just move the stuff dealing with X and Y over. Okay. And then I'm going to go ahead and I'm going to divide by C to just get this piece on its own. And that just takes each of these and divides it by C. Okay. And then realistically, A and B and C are still all unknown. So instead, what I can do is just call these a different variable, capital A and capital B. Okay. And then I can go ahead and move this to the other side. So this gets the Z by itself, and this is the initial Z value. This I'm calling A, and this I'm calling B. Okay. And this gives us the equation of our tangent plane. This point is known, this point is known, this point is known. It's just the values of A and B that are unknown. But this is starting to look a lot like our equation for a tangent line. Initial point, derivative x minus x naught. Here we have the initial point, x minus x naught, y minus y naught, because it's two variables. And these are going to turn into those partial derivatives. So what I can do is I can utilize my knowledge about those lines, L1 and L2, and their slopes to show that these are exactly the partial derivatives. So if I look at line 1, because this is parallel to the x-axis, we're really going to let y equal the y coordinate of that point. So it gives us that horizontal line. So if I do that back here, if we restrict ourselves to the line y equals y naught, that is a horizontal line, so this is parallel to the x-axis. That's line 1 in my image. Then this equation becomes the following. We have z is equal to this initial point plus a, and then the y is restricted to y naught. So this whole component ends up going to 0. So we get z has to equal this partial, or this initial point, plus a times x minus x naught. And we know the slope of this line because this is the one that runs parallel to the x-axis. So this line has to have slope, which is the partial derivative. So this line must have slope which is the partial of f with respect to x at that particular point. So this tells us the value a I'm searching for is exactly the partial with respect to x at that point. And then if we do the same thing, if I restrict myself to that vertical line through this particular point, so pointing in the y direction, well, that particular line would have x equaling the x coordinate of that initial point. So that will just give you b, and it will tell you that the value of b is going to end up having to be the partial with respect to y. So we end up finding that these constants have to be exactly what we want. So in a similar manner, if we restrict ourselves to x equaling x naught, which is line 2, we get that the z component will be that initial point plus b times y minus the y coordinate. And the slope of this line has to be the partial with respect to y. So the component b must be exactly that. Okay. So if I have a function and I'm looking for the equation of that tangent plane now, this isn't a level surface, this is just a function, I can find those exact components using essentially that gradient vector. Right. So what we ultimately get is if z is a function of x and y, this has continuous partial derivatives then an equation of the tangent plane at the point x naught, y naught, and then the z coordinate is the following. Our z value will be the initial z value plus the partial with respect to x at that particular point times x minus x naught, and then the partial with respect to y at that point times y minus the y coordinate. So it gives us the equation of the tangent plane. Okay. To relate this to what we did with level surfaces, just to kind of show you quickly, if you have this equation, what you can do is just rearrange it. This tells you 0 is a function of xy minus z. That's exactly a level surface. So the gradient vector here would be the derivative of this with respect to x, so that would just end up being the partial with respect to x. This would be the partial with respect to y, and then the partial with respect to z would just end up being -1. So all you would end up getting is you would evaluate this at that particular point, and then your equation of the tangent plane would be that partial times x minus the x coordinate of the point. Then we've got the partial times y minus the y coordinate of the point, and then minus 1 times z minus the z coordinate of the point, which is the initial point, equals 0. So you're really just moving this to the other side, and it gives you z minus the initial coordinate of the point is equal to those partials, and then you would add this over. So exactly the same equation that we came up with last time. It's just a very specific instance because our level, it's not a level surface, it's given us that function z equals f of xy. But same exact concept. So I'm gonna go ahead and erase all of this because we don't need this for this particular section. Okay. So this gives us the equation of the tangent plane now, and what that lets us do is for points near x naught, y naught, we can go ahead and figure out what is z roughly equal to. And so it's linear because the x and y terms are first degree powers. So this is the linear approximation of f at the point x naught, y naught. So L of xy is going to be exactly this tangent plane. And then we can say our function is about equal to the tangent plane near that particular point. Okay. So let's go ahead and let's try an example of this. Again, in practice, it is not as complicated as it looks because we just have a lot of different variables and components going on. So the example we're going to start with is we're going to find an equation of the tangent plane to the function z equaling natural log of x minus 2y at the point 3, 1, 0. So this one already finds the z component for us, but if you plug in 3, 1, that would be natural log of 1. The z component is 0. So it just does the work for us. We don't need to find the z coordinate. What I do need to do is I need to take the partial derivatives of z, or essentially find the gradient. So if I go ahead and take the partial derivative of this with respect to x, I get 1 over the inside function. And then I've got to take the derivative of this with respect to x, which is thankfully just 1. So same thing ends up happening for the partial with respect to z. You get 1 over the inside function. But when I take the derivative with respect to y, I get a negative 2 popping out. So we get a negative 2 in the top. Okay. These would tell us the slopes of the lines in these directions at any point, but specifically we want to find the slope at 3, 1. So if I plug that in, my x is 3, my y is 1. So this slope thankfully ends up just being 1. The slope in the y direction would be negative 2 over 3 minus 2. So this slope is negative 2. So I have everything I need to find the equation of the tangent plane. The z values on the tangent plane are given by the function evaluated at 3, 1, which you can just call z because they didn't label it f. So it's z evaluated at 3, 1, plus the partial of z with respect to x at that particular point, times x minus the x coordinate, and then the partial with respect to y, and put in that this was at 3, 1, evaluated at 3, 1, times y minus the y coordinate of the point. So if I plug 3, 1 into the function, again, they already tell us that is 0. Partial with respect to x at the point is 1, so times x minus 3. Partial with respect to y at that point is negative 2, and then we get y minus 1. If you left it like this, no problem. You can make this easier because if you do have to evaluate it, it's a little bit nicer if you just distribute everything out. So distributing that minus sign and then grouping the like things. This is x minus 2y minus 1. So this gives us a very nice form for the equation of the tangent plane at 3, 1. So it doesn't say to find this or approximate this, but what you could say is that natural log of x minus 2y, which is our function, is about equal to x minus 2y minus 1 nearby the point 3, 1, 0. Because I may not be able to evaluate natural log, but I could plug in those values of x and y very easily over here. Right? So this leads into a concept because back up here, we talked about these need to have continuous partial derivatives so that I can actually evaluate these partials with respect to x and with respect to y. This actually gives us our definition for differentiability. So we know it has to deal with the limit, but we have an easier way that we can talk about differentiability. So we say a function f is differentiable at the point x naught, y naught, if both the partials with respect to x and with respect to y exist near that point, and they are continuous at that point. Okay. So to go back up here, because I have no issues with these functions evaluating at 3, 1, that is not a point that's not inside the domain of these partial derivatives, we can say that f is, or the function z is differentiable at the point 3, 1, 0. So let's do another example like this, and we're going to actually use the tangent plane to approximate a value. So we're going to go ahead and we're going to show that the function f of xy, which is x over x plus y, is differentiable at the point 2, 1. And then we're going to find its linear approximation at 2, 1. Once we find that, we're going to use it to approximate the function at 2.1, 1.1, because this point is nearby to 1, okay? So I need to take partials of this thing. So I'm going to go ahead and just rewrite this to make my partial with respect to y a little bit easier. If I go to take my partial with respect to x, unfortunately I am going to have to do quotient rule because we have x in the numerator and denominator. So if I take the partial with respect to x, we have low, derivative of the high is 1 with respect to x, minus high, and then derivative of the low is also 1. And then this is all over low, low. So this ends up just being, and I put 1, this should be a y, low d high. This ends up being x plus y minus x in the numerator over x plus y squared. So it gives me y over x plus y squared. Okay. And then if I take the partial with respect to y, thankfully that's a little bit easier because I just have this dealing with y. So applying our power rule, the power gets brought down. We decrease the power by 1. And then chain rule, I'd have to take the derivative of the inside with respect to y, but that thankfully is just 1. So this ends up equaling negative x over x plus y squared. Okay. So if I look at these two partial derivatives, the only time we're going to have an issue is if the denominator is equal to 0. So x is really negative y. Well, that's not the case for this particular point. So both of these functions are continuous at 2, 1. This value does not pose an issue to us. So because they are continuous at 2, 1, f is differentiable at 2, 1 because both partials are continuous. Okay. So that shows the first part because it does ask us to show this function is differentiable at 2, 1. Now I want to find the linear approximation, but really this is kind of already set me up for that because I've got to evaluate both of these at 2, 1, and I also need to find my z value at 2, 1. Okay. So if we look at the function evaluated at 2, 1, the x is 2, the y is 1. So our z value at that point is 2/3. If I find my partial with respect to x at 2, 1, that is y over x plus y squared. So that's 3 in the bottom squared. This is 1/9. Move these over a little bit to find z or y. Plugging in these values, that's negative x over x plus y squared. So that ends up being negative 2/9. So I have everything I need. We can now find the linear approximation. So L of xy is going to be f of 2, 1 plus the partial with respect to x evaluated at 2, 1 times x minus the x coordinate, partial with respect to y at that point, times y minus the y coordinate. So the first part is 2/3, then we've got 1/9 times x minus 2, and then negative 2/9 times y minus 1. So that is my linear approximation, and again, this is just telling me my z values are about equal to this. So what I can say is that my function is about equal to this tangent plane. So if I want to approximate, going way back up here, 2.1 over 2.1 plus 1.1, I can instead plug everything over here. So our function at 2.1, 1.1 is about equal to 2/3 plus 1/9 times 2.1 minus 2 minus 2/9 times 1.1 minus 1. So 2.1 minus 2 is 0.1. That is just 1/10. And same thing over here, 1.1 minus 1 is 0.1 or 1/10. So this is about equal to 2/3 plus 1 over 90 minus 2 over 90. And then I'm going to trust that you could condense this fractions. This is about equal to 59 over 90. So what we're ultimately saying is, remember, our function that we started out with is x over x plus y. If I wanted to find what 2.1 over 2.1 plus 1.1 is, it's about equal to this fraction. So much simpler to plug into, and this is what your calculator is doing behind the scenes on a lot of your stuff, okay? So I really just have one more application now of this. We should feel pretty confident about tangent planes, how to find them, what the normal vector looks like. The last thing we're going to do is talk about a normal line. And so if I scroll all the way back up, really the normal line is just going to be the line going through that point, and you need that normal line, or you need the direction vector of it. So for a line, all you needed was the point and the direction it was heading. But we know the normal line just deals with the gradient vector. So really all I'm going to do is use the gradient vector to find those components. So to just kind of summarize all of that, if you're finding a tangent plane, you can immediately find the normal line too, because they have the same direction vector. So the normal line is the line passing through the point x naught, y naught, and then whatever the z coordinate is, that's orthogonal to the tangent plane. With direction vector which is the gradient at that particular point. Okay. So to just use this last example as a kind of quick input, this would be the x and y component of that gradient vector. And what you would need to do to find the z component is exactly what I showed you before. This is z is equal to x over x plus y. Just move that over. 0 is x over x plus y minus z. So the direction in that z component of the gradient vector would be the partial with respect to z, so it's -1. Okay? So your normal line would have the direction vector 1/9, -2/9, and then -1. So what I'm going to do is I'm going to show you a different type of example where I don't necessarily have z solved for itself. I have y in terms of x and z. So for this example, we're going to find the equations of the tangent plane and normal line to the function y equals x squared minus z squared at the point 4, 7, 3. Because this would be exactly the same if you just rearrange this to be like something like that instead. Okay? The process will not change. So all I'm going to do is I'm going to move everything to one side. So if y is equal to x squared minus z squared, moving that over and just putting them in order for convenience, 0 is x squared minus y squared minus z squared. So the function that I'm working with in this case is x squared minus y minus z squared. Okay. So the gradient of this vector is the partial with respect to x, the partial with respect to y, the partial with respect to z. Okay. And then specifically, I'm looking at the point 4, 7, 3. So we plug in 4 for x, giving us 8. The y is just -1. And plugging in z is 3 gives us this vector. Okay. So this is the vector that is normal to our tangent plane. So that gives us the components that go in front of the x, y, and z. And then the normal line has this as a direction vector and passes through 4, 7, 3. So I can immediately come up with my equations. Okay. So the tangent plane has normal vector (8, -1, -6) and passes through 4, 7, 3. Okay. So its equation is the x component of the normal vector is 8 times x minus the x coordinate. The y component of the normal vector is -1, y minus the y component. And then the z component of the normal vector is -6 times z minus the z component. And that equals 0. Okay. And then you could absolutely go ahead, distribute all these values, rearrange it, put the constant on one side. If you do that, you would have 8x minus y minus 6z, and all of the constants would move to the other side as 7. Okay. So this is the tangent plane. Now what we did before was basically if you just take this equation and solve for z, that gives you the linear approximation. Doesn't change anything at all that we've done. But now that I also have this, we can find the normal line. So the normal line has direction vector -8, -1, or sorry, +8, -1, -6, and passes through 4, 7, 3. So its equation is the following. Lines are typically vector functions. So you take the initial x starting point and you add the slope times t. You take the y starting point, the slope times t. The z starting point, slope times t. And then again, you can also create the symmetric equations and everything else from here, so you can look back in your notes if you need that. But this is the normal line through that particular point. Okay? So again, this does not change anything at all. Going back up to this example, if I asked you to find, always does this, there we go, let's get rid of all the, go. Okay, if at this point I asked you to find the equation of the tangent plane and the normal line at that particular point, you would just say, great, z is equal to this. So ultimately 0 is equal to this minus c. So your function of x, y, and z would be exactly this one. So the gradient vector would be exactly these partials you found. And then your z component is -1. So the gradient at that point would just be exactly these values you found. This would be 1/9 for the x, -2/9 for the y, and then the z is -1. So those would be the components in front of x, y, and z, and then you'd have x minus this x coordinate, y minus this y coordinate, and it would be z minus this z coordinate. You'd get that equation equals 0, and then you would go ahead and just solve for z, and you would see it would end up being exactly this here. So it does not change the process at all. This just makes it so that you can easily see the connection from Calc 1, and you can also see that this represents a Taylor series of multivariables, okay? But this process is just much easier over here when I'm trying to find the normal line too. So I have that direction vector. So if you need a refresh on how to find planes and how to find lines, go back, look through your notes. We're just finding very specific ones here now involving that surface. So it's going to involve those partial derivatives or that gradient vector.